This is going to be the first in a not continuous, but a continually interrupted series of lectures on algebraic geometry. None of this is like original notes or anything. It's mostly going to be a guided reading of Hartshorne, but I'm going to try to interject some of my own knowledge and my own reading on the subject, fill in those gaps where the reading might be a bit sparse. So if you guys want to like fill in on the stuff that we learn in the talks later on so that you can show up for the next talk and not feel like there was a 2-week gap between them, just try and go read some Hartshorne. I'm going to be starting with the first chapter on affine varieties today. And we're going to stick to the affine case. I'm not really going to be talking about projective things in this series of lectures. I'm mostly just going to be talking about the affine case. So, if that's what I'm going to be doing, the first thing I ought to tell you is what affine space is. In the beginning, we begin with fields. Later on, the discussion of algebraic geometry is going to be focused around commutative rings with unity. And so whenever I say ring, I will always mean a commutative ring with unity. But at the beginning, we're going to be discussing fields. And this goes back to the classical roots of algebraic geometry. It was about studying the solutions of polynomials. And we posed polynomials, classically, over fields like the rational numbers, or the real numbers, or even eventually the complex numbers when we were looking for something that was algebraically closed. So this is the historical context in which algebraic geometry arose. But over time, as we came up with new definitions and made the subject of algebra more rigorous, we came to a more concrete understanding of what studying the solutions of a set of polynomials actually means. So first things first is the space where we will start off. If I go ahead and take a field F and take its Cartesian product with itself n times, hopefully we're all familiar with the fact that this makes a vector space, an n-dimensional vector space, over this field. And in fact, all n-dimensional vector spaces over this field will be isomorphic to this one. Affine space, affine n space, over our field F is going to share the same underlying set of points as Fn. So the points of this space are the same. But when we're talking about this space, there is a special distinguished point of Fn, the vector space, which we would like to no longer be distinguished anymore. We would like all of the points in space to be the same. In a vector space, the origin is not the same as every other point. He's special. And so we need to forget the origin, and that's exactly what the affine space is. Affine n space is just Fn, where now 0, 0, 0 n times doesn't play the role of an origin anymore. All points are equally special. And you can only talk about vectors now as differences between 2 points. So if P and Q are points in my affine space, I can associate a displacement vector from P to Q that plays the role, it's like the vector in the original space that starts at P and points at Q, except I can't just add and subtract arbitrary vectors. I can only add and subtract certain vectors to certain points. So for every single point in space, I will have an entire new Fn vector space of points, Fn vector space, excuse me, of vectors that I can add to my point. And now that will be able to get me to other points in my vector space. So this is illegitimate. It's just sort of for intuition. This is what we actually have. At every single point in affine space, an independent vector space of displacement vectors along which we can travel.
I apologize. So An event is just the affine space over...
Yeah, affine n space over our field F.
So you identify all scalings of a vector with a single vector?
All scalings of a vector with a single vector. Yeah, no, we're not. This is affine, not projective. So in the case you're describing, we would add an additional coordinate, and then we would identify by scalings, non-zero scalings, but I won't be touching the projective case at all. I'll only be discussing the affine case. So, okay. So this is the setting. This is the general simple space on which we live. And this is where we're going to be able to define polynomials, the polynomials that we will be solving, whose solution sets we'll be studying. And there are two ways that we can think of them. We can either think of them as just expressions that we can write down in the polynomial ring over the field in n variables, n space, so n different variables. This is just how you would have normally studied polynomials in your algebra class without ever having to talk about a space underneath them. You wouldn't have even thought about associating a space. Well, in addition to that, we can also think about functions from affine n space to the field, which have been generated out of the field operations addition and multiplication. So, as well as the coordinate functions and the constant function 1. This is exactly like constructing the polynomials here, but now I'm doing it out of functions. I can take individual coordinate functions, they represent the individual variable. I can multiply them together, I can add them, I can scale them by elements of my field. That's what this one's doing for me. And so that allows me to think of the polynomials on affine space in these two different ways. Once as these formal expressions in these variables, which is very nice for manipulations in terms of ideals and other things. I have things like Hilbert's basis theorem that I can and will throw at that soon. And now also as functions, I can talk about stuff like zero loci. Right? I can ask the question, what are all the points in this set that this function maps to 0? Which is not, I can do something similar to that here, but this is a much easier way to present it. This is just nicer to work with for that. Okay. So I mentioned something a second ago about Hilbert's basis theorem. Where does that come in? Well, first, I'm going to tell you about the sorts of sets that we're going to be studying, or one of them at least. And they are all going to look like this. Z of p is equal to the set of all points in affine n space such that p of this point is equal to 0 for all polynomials in this set p. So that's what this p is. It is a subset of my ring of polynomials. And you might be worried. You might think a subset, like not a finite subset, just a subset. It could be like an infinite subset. You could be asking me to solve infinitely many algebraic equations. Isn't this algebra? And it turns out that, yeah, a subset. No quantification on its size. And yeah, we are still doing algebra because no matter what, it's always going to be the same as solving finitely many polynomials. So, first things first. The zero set of all points for which the polynomials are all 0, is identical for both a set of polynomials and the ideal that it generates. This is not too hard to see. In order to come up with the elements of this guy, you take finitely many elements of this guy and then write combinations, linear combinations in other elements of our polynomial ring over them. So it's pretty easy to see that those are all going to vanish because I'm multiplying things where one of the factors is going to be 0 and then adding them all up. They're all going to be 0. So that's my first thing I need. The second thing I need is called Hilbert's basis theorem, which is one of the named theorems of algebra. And it's one of the ways that our forefather Hilbert made the theory of algebraic geometry, as we have it right now, possible. His named theorems are crucial to the setup of classical algebraic geometry and to the sort of mindset that leads to the modern algebraic geometry. So Hilbert's basis theorem, and there are, I will give you some extra terminology. So it says that the ring of polynomials over a field with finitely many generators, like we've got here, is what we say Noetherian. And what that means is that if I is an ideal, then there exists a finite set of polynomials that generates this ideal. Okay, what the hell does all of that have to do with what I was saying before about us still living in the land of algebra? Well, I just learned that any ideal is equivalent to the ideal, any ideal of polynomials is equivalent to the ideal generated by finitely many polynomials. And whether I just ask those finite polynomials to vanish or the entire ideal to vanish is of no consequence. So, for an arbitrary set, it will be equal to the vanishing set of the ideal it generates. This will be generated by finitely many things. It will be the zero set of those finitely many things. So we're only ever studying the zero sets of finite collections of polynomials. So even by introducing this z on arbitrary subsets of polynomials of arbitrary size, that might seem inherently weird and infinitary, Hilbert's basis theorem rescues us from that. So we don't have anything to worry about there. Oh yes, sorry, excuse me, you're totally right. So f1 all the way up to fn equal to I. Okay. So what can we do with this? What does having access to all of those sets actually buy us? Well, it gives us better insight into the structure of these, what are called algebraic sets. These things, which are zero sets of collections of polynomials, we call them algebraic sets, and they have a particular structure as subsets of affine space. It's a structure which is at least as strong as the structure of a frame, where a frame is the structure that a topology in a topological space has. It's something that's closed under arbitrary joins and finite meets, something that contains the trivial thing on both sides, the biggest and smallest element. So let's see that that's actually the case here. So first things first, I want to, and actually it's not exactly going to be, it's going to be the reverse of a frame. The frame is normally what the open sets satisfy. It's actually the algebraic sets are going to satisfy the structure that the closed sets satisfy, which means the opposite of what I mentioned a second ago. Instead of arbitrary joins, which would have been arbitrary unions for us, we're going to do arbitrary intersections and finite unions. So I just have to show that the union, I have to show that the union of two algebraic sets is algebraic, and then I have to show that the arbitrary intersection of two algebraic sets is algebraic. But this is nice and easy. Hopefully it won't take too many of us to be convinced that if I were to take the set, and what this means is it's the set of all elements that I get by taking one of the elements of the first guy, one of the elements of the second, and then multiplying them. This will now be a set of polynomials on which this union corresponds to the vanishing set. Is that clear to everybody why that is? It's also hopefully clear why we can't necessarily do better than finite unions. I can't multiply infinitely many sets together, so finite unions are the best that I can do here. Okay. What about intersections? So arbitrary intersection. Okay, and so let's think about this. We have a bunch of different zero sets of polynomials, and we want to find the set of polynomials that will give us their intersection, the one where all of the polynomials are 0. Well, that kind of does it. All of the polynomials. What set contains all of the polynomials? The union of all of them. It's not a whole lot of thought involved in this bit. This would all have been impossible if we required these to be finite sets, which would have been the setting from classical algebra. But knowing that we're allowed to use infinite sets makes all this very easy. So yeah, very clearly a set of polynomials. So yeah, intersection of algebraic sets is always algebraic. And then the zero set of 1 is the empty set. 1 never vanishes. And the zero set of 0 is very clearly all of affine space, because it vanishes everywhere. So there we go. With this, what we've learned is that these sets, these algebraic sets, have all of the properties that we would need to call them the closed sets of a topological space. And so that's what we do. When structure falls out at us from the cosmos, it's not a mistake. It's not an accident. There are no coincidences. That should be important somehow, and so it gets incorporated into our framework. So we have this thing now called the Zariski topology. Which you can think of as now being something that comes along with affine space. When I say affine space now, I mean not just the Fn without its origin, but Fn without its origin with the Zariski topology. So Zariski topology. And as we just saw, U is open. If the complement of U is an algebraic set. Okay. So there we go. That's the topology that we're going to be using. And it's a whole lot different. If you have studied topology before and you've seen some classical examples of nice topological spaces like the real line or the complex plane, you would find this topology to be quite strange because it is very coarse when compared with those topologies. So as an example, if we were to just talk about the Zariski topology on affine 1 space, so this is just the field where we've forgotten what the origin is. It's the affine line. Closed sets that aren't the entire space, well, they have to be generated by finitely many polynomials. So that means I only get one root. I only have one variable, and finitely many polynomials in that one variable. There's going to be finitely many points on the line. So closed, non-trivial sets are unions of finite points. And so, in particular, if F is an infinite field, something like R or C, or any number of other fields that have similar properties, well, then these can't be Hausdorff anymore, for the simple fact that there's going to be infinitely many points in the open set determined by any one of these closed sets. And the other open set could only exclude finitely many of them. So they got to overlap at least infinitely many times. So Hausdorffness, which is the thing that guarantees the uniqueness of limits, that's out of the window. We don't have it here, not in the Zariski topology. It's still Frichet, though. It still satisfies the T1 axiom. Because for any pair of points, right, I can always find an open set that contains one and not the other. Take the polynomial that vanishes at that guy. That guy will determine an open set. It will contain one of the points and not the other. Do it for both of them, bam. You could do it for both of them. It's a Frichet space.
It's not T2, you said?
Not T2, yeah, not Hausdorff. Limits are not necessarily unique. Indeed, right? Okay. Teeny bit more topology here before we get back to anything that resembles algebra. So a subset of a topological space is called irreducible or hyperconnected, depending on where you are. Some people, like topologists, general topologists, generally say hyperconnected, and algebraic geometers generally say irreducible. They both mean the same thing. If it is not the union of two proper closed subsets. All of its overlaps have to have an interior somehow. They have to have space around inside of them. Union of two proper closed subsets. So, as an example, the affine line. The affine line is irreducible. I definitely can't write him as a union of two closed things. The non-trivial closed things contain finitely many points. If f has infinitely many points in it, no dice. Can't happen. The only other irreducible things in the affine line are just points. The only thing that's irreducible on the real line is just points. The entire real line is not irreducible anymore because the real line can be written as the union all x which are greater than or equal to 0 and all x which are less than or equal to 0. That's a pair of proper closed sets. It's equal to the entire R when you take their union. So R is not irreducible. So this is kind of where the coarseness of the Zariski topology actually comes in hand. Because irreducibility is going to be important for our definitions of certain spaces. It's going to have an important algebraic counterpart when we study their coordinate rings. But the finer topologies that we're used to working with in general topology, they have too many open sets that are too small, that all don't touch each other. And the result of this is it's very difficult for such a space to be hyperconnected unless it's just a point. And then who cares? So.
In your definition of irreducible, can these two proper closed subsets overlap?
Yeah, that's totally fine. There's no problem with them overlapping.
Okay.
Okay. So I mentioned already the idea of a coordinate ring. So I want to bring that up really quickly. So we've already talked about the idea that I can generate an algebraic set using any one of these sets of polynomials, right? I don't have to rewrite it again. Everybody is clear on that. These are algebraic sets. for some subset of polynomials. Subset. Okay. They are spaces in their own right. And just like we were able to define the polynomials on all of affine space, we should also be able to define the polynomials on these spaces. What should the maps on these spaces into field look like? And the simple answer is, so the coordinate ring of our algebraic set is just going to be the quotient of our original set of polynomials. So if you like, all of the polynomials that we could have written down in ambient space, subject to the relations that hold on our zero set, all of the polynomials that vanish there. Which, if you're suspicious of this, if you think, oh, that's BS, no, you could totally do it. Try it. Take the sphere in R3. Right? You could totally write down polynomials in terms of x1, x2, x3, x, y, and z. Yeah, not all of them are independent coordinates on the surface of the sphere, but that doesn't stop you from writing down polynomials relative to them. You just have to remember that not all polynomials you can write down in x, y, and z are unique. Some are the same because of the relations that hold. In particular, right, on the sphere, that relation holds. So that's equal to that. So the ideal that defines our zero polynomial, we just quotient by that. That gives us the ring of polynomials that live on it. And this is our bridge from geometry to algebra. We take a zero set, a space, and we send it to an algebraic thing that lives on it. The amazing thing that we see in algebraic geometry is that under certain circumstances, this map, this sending of geometry to algebra, is one-to-one and preserves all the information. And so it allows you to work on either side of that map, either on the geometry side or the algebra side, depending on which you prefer, or which is easier for the problem.
Sorry, so this quotient ring is, how should we interpret this quotient ring?
It's the ring of all polynomials that you could already write down in the ambient space, but subject to the relations that hold on the zero set. So if you like, right, on the sphere, I could have written down.
Oh, you could mod it out by x squared plus y squared.
Exactly. I could have written this function down on the sphere, but it would have just been the constant 1 everywhere. So I have to remember, oh yeah, some of these functions aren't unique, aren't uniquely represented.
So just now, I should think about this ring of polynomials when we quotient out as polynomials on some algebraic curve, some algebraic.
Exactly. There's the polynomials that live on that space. And you could actually go and justify it. Like you could parameterize local patches of that space and find out that these things really are polynomials that way. This is just way easier. Yeah. It's way, way easier to do this. Okay. And now the last thing that I get to define here before I bring up my next named theorem. And I'm making really good time. Okay. So we just saw the map that went from geometry to algebra. So for any oh, actually, you know what? Let me define variety first, and then I'll talk about this. 1 second, sorry. Yeah, that's, oh my God. Okay, so affine varieties. Okay, so we've seen algebraic sets. We've seen the definition of irreducible. All an affine variety is an irreducible closed subset of affine space. So an algebraic set, but which can't be written as the union of two proper subsets, and neither of them can be empty. That should be in the definition. Is equal to its own radical, and then what this situation is saying is that now if I define the map I, which associates subsets of affine space to, now this is going to be an ideal. It's going to be all polynomials that vanish on this set. This gives me a mapping from subsets of affine space to ideals, such that PS is equal to 0. And now, if I take the ideal of functions that vanish on the 0 set, some ideal j, and j is radical, then this mapping is 1-to-1. In other words, the algebraic subsets of affine space are in 1-to-1 correspondence with radical ideals of the polynomial ring. So that's how we can identify, on the algebra side, the closed sets that we're studying. They're always going to correspond to these radical ideals. So J radical. But there's more we can say. Someone was about to ask something? No? Okay. Yeah, there's more that we can say. Not only can we identify when these sets are algebraic sets from their associated ideals, we can furthermore associate certain algebraic sets to even specialer ideals that tell us that they're actually varieties. So it turns out that if J is prime, so a prime ideal, then the associated algebraic set is a variety. It's irreducible. And that goes both ways. It's both, if your ideal is prime, you are a variety, and the variety of a prime ideal.
So are you saying that J is equal to the radical of I of S?
J is equal to the radical of I of S.
Is that what you mean?
No, J is equal to the ideal of polynomials that vanish on it if J is radical.
Okay, J is a radical ideal of some ideal.
If it's a radical ideal. It doesn't have to be of some other ideal. It's just a radical ideal. A radical ideal is one that is the radical of itself.
Okay.
So if I take its radical, I just get the same thing back.
So generically, if I had a generic ideal J.
Yeah, then you would just wind up. You would wind up with the notation that they use as this. It doesn't just mean square roots. It means all roots. Yeah. But now, yeah, if J is equal to rad J, then we furthermore get this. And that establishes the 1-to-1 correspondence that it reverses inclusion between algebraic sets and these radical ideals in our polynomial ring. So that's what the Nullstellensatz buys us, the so-called theorem of zeros. It is exactly what underpins this 1-to-1 correspondence between algebra and geometry that's occurring in algebraic geometry. That thing that allows us to translate from one book to another.
Is this the strong version of Nullstellensatz? Is there like a strong or weak version, or that strong and weak version of Hilbert basis?
I think you might be, because yeah, I've never seen other versions of this, but maybe I just haven't gone far afield enough. Who knows? Okay. So there we are. I mean, that's pretty cool, right? We started by studying the polynomials and the solutions of polynomials that are, the people who created mathematics and invented the objects that we studied. They studied them long ago, and we've come up with this great apparatus which allows us to translate problems about those things into pure algebra problems. So what gives? Why would we generalize to schemes? Why isn't this good enough? Why not just stop here and just keep studying these things forever? Right? I mean, they're cool. There's plenty of cool things that you can say about them, plenty of good theorems that can be found out. Not all the work has been done on them, certainly. So what gives?
So you're saying that we're going to eventually not care about ZFP? We're not going to care about ZFP as zeros of some.
Well, that's eventually when we come up with what our definitions of space are, it's going to be very different from this. But it's going to be motivated by the tools that we have access to. Because this is the thing that we should be mindful of, right? We were handed these lovely objects to study by the ancients, and over the hundreds and thousands of years that people have had access to them, they've developed these incredible tools, and now we can bring these tools to bear on these very nice spaces. But we got these great tools. And maybe they don't only just apply on varieties, right? Maybe these tools have a further field of application than just the original spaces we invented them on. That is, we're going to change the question up. Instead of asking, what are the right tools to study our space? We've got the tools already. We're going to ask, what spaces can we study with our tools? When we go through the correspondence between varieties and prime ideals, and then we go ahead and take the quotients to go to coordinate rings, what we wind up finding is that the coordinate rings of affine varieties always have the following three properties. I'm using K here for some reason. I'm going to stay consistent. They are all algebras over the field that we started with. They have no nilpotent element. Oh, actually, you know what? I'll do this one next. They're all finitely generated. That's a nice condition. Everybody loves finite generation. It makes life so much easier. And they have no nilpotent elements. They have other properties too, but these are...
What are they?
These are the coordinate rings of affine varieties, so the things that you get by quotienting out by the prime ideals. They have other properties that are actually very important for why schemes look like why they do, and not as much like varieties as you might expect. All of the coordinate rings of affine varieties are, I believe, what you call Hilbert-Jacobson rings. That means that their prime ideals are all the intersections of their maximal ideals. Maximal ideals are associated to points in algebra, and so you can think of this as a space where it's got enough points to determine all the functions in and out of it. But schemes end up having not enough points, and they need things besides maximal ideals, prime ideals, to deal with this. So for those of you who know, you know. Okay, so these are the conditions that are currently placed on the algebras that we study. And because of that, we're not making full use of all of commutative geometry. There are other things that could theoretically be coordinate rings that we could still use the exact same tools of commutative geometry to study, but they never arise as the coordinate rings of any objects. So for instance, maybe like the initial ring, I don't know, like the most basic, that would be a nice one to be able to study, but that guy's not an F algebra. By the way, this explanation is taken straight from Richard E. Borchard, who is another great lecturer, teaches lots of different algebra subjects and has an AG lecture on YouTube, which I would highly recommend. But these are the reasons that he presented, and I think this is a really nice, concise way of presenting it. So yeah, so we can't use that to study, we can't allow all of our examples to satisfy this if we want to study something nice and basic like Z. We also can't study something like the field of fractions if we're forcing ourselves to only consider finitely generated examples. So this guy can't possibly be maintained if we're to study things like the fields of fractions or other interesting localizations which lose this finite generation property. And then no nilpotence. Why would we care about that? Well, imagine a situation like this. So this is a quotient that arises when studying the intersection of the standard parabola, y is equal to x squared, with the x-axis, y equals 0. And traditionally, in classical algebraic geometry, in order to make sense of this, in order to make it a space, and this a coordinate ring, because this has nilpotent elements, they would just say, toss away the fact that this is squared, and just say that this is the coordinate ring of the variety. But when you do that, you lose information. You forget that that intersection was a double point. You say that it's a single point now, and we know that's wrong, and so counting theorems around multiplicity can't use that. They can only use that if they want to succeed. And counting theorems are really important. So we really care about the ability to record information like multiplicity. And if denying nilpotence is what's preventing us from doing that, then that's a no-go. We're going to have to stop doing that. And with those things, we have now opened ourselves up to the entirety of commutative ring theory. And by commutative ring, I mean a commutative ring with unity, because it's the only other restriction I'm making on it. We should be able to associate to every other commutative ring with unity some space such that that ring can be thought of as the ring of coordinates, the ring of polynomials that lives on it. Okay. So, I'm going to spend the rest of this moment that I have now just introducing the idea of a sheaf, because it's going to be very important when I bring up schemes here in a bit. But if you've never seen it before, it's a big scary thing, so I want to introduce it to you now, let you go and maybe read about it in Hartshorne and become gently introduced to the idea if it's at all possible. They're really, really important in lots of subjects besides just topology, though. Sheaves are really, really big. Okay. Okay. We say that F is a sheaf if, I guess we'll go fully general here. So for every single open set in my topology, F sends us to some set. For every subset inclusion, there is a restriction morphism, which takes me from the bigger guy to the smaller guy. And since these are just sets, the restriction morphism is just a set function. It doesn't have to have any special properties. And now for any triple inclusion, it doesn't matter whether you restrict all the way down from W to U, or if you restrict from V and then from V to U. So, and I should have done this. V. Oh, wait. WV, UV. Hopefully I got that right. Yeah, that's right. Okay. So, no, it isn't. Okay, I'm losing my mind. Sorry, these things are switched, and that automatically makes my brain stop working.
Isn't f of u supposed to be a group? Send you into a billion?
If it's a sheaf of abelian groups. Sheaves don't have to be sheaves of abelian groups. They could just be sheaves of sets.
Okay.
So, and then let me make sure that I'm actually doing this right. Otherwise, I'm going to lose my mind. So we go from FW into FU. Yeah, it's just because I'm getting a PhD doesn't mean that's not too much for me to think about. Okay. So that's, well, okay, I got the easy order correct. That's true. I did do that. But that means that this one now, because I have this one showing up here, that one should have been that one. It was exactly the opposite of what I did, which was perfect. Okay. So there we go. We have this. This is a commuting triangle. I haven't written it like that, but that's what this is. So far, this is just a pre-sheaf. A pre-sheaf is just something that has this property. It gives us a set for every open set. For all the inclusions, it gives us a morphism. Every single triple inclusion has to end up having this commuting triangle occur. And now to make a pre-sheaf into a sheaf, we need only give it one more condition. So you're right, Lewis, that, or rather, it's good that you point out that, yeah, I'm just doing sets here. Theoretically, this could take values in any category. So you could have a sheaf of objects in any category. In particular, what we're going to be using here in algebraic geometry is sheaves of rings, not sheaves of just abelian groups anymore, because the additional ring structure will be important, and it's also something we have, right? We have it when we're talking about the coordinate ring of functions, of polynomial functions. So if we have that structure, we damn well better use it. Okay. Sheaf condition. Okay. A pre-sheaf F is a sheaf if it satisfies a particular gluing relation. So for all open sets in the topology of my space and all open covers of that open set, such that they come along with, together with, elements corresponding to the sets from those opens, or the category object corresponding to those opens. So Fj in F of Uj, such that we need a compatibility condition. So such that row of, and this is from this, so it's going to be U, I, and Uj, not U, I, this acting on F of I is equal to, I'm doing that right, correct? Yes, I am doing that correct. Excellent. This looks super crazy like this, but this restriction morphism from the pre-sheaf, it often is literally just restriction of a function. It's just taking a function and restricting its domain. And in that case, what this is saying is that when I restrict these two different functions down to the intersections of their domains, they are the same function. Okay? And then the condition is that there exists a unique element of the big open set, the one that we were covering, such that the restriction down to, so the restriction of this guy down to any of those open sets in the cover was just the section element associated to that cover. So I took a bunch of things defined on open sets that covered my space, and I turned them all up into one big thing, and I'm allowed to do that because they all agree on overlaps. They all agree on intersections. So the classical example of this is the sheaf of continuous functions on a topological space into any other space. That will give you a sheaf, because continuity is a local condition. If you're continuous at every single point and you agree on these overlaps, then we can use the gluing lemma to just glue you together. And I think, I'm not going to get too far into the next thing that I want to talk about, so I'll just wrap up and leave it open to questions from here. So, and I won't erase anything yet. So, any questions on anything? Yes.
So right now we're trying to define these coordinate rings in terms of sheaves, right?
Right. So right now I'm defining sheaves so that next time we can see that there are sheaves that live naturally on our varieties. Right. I want to show that the structure of a scheme was really part of a variety all along. We just didn't see it yet because we didn't know the definitions. But I want to discover the structure in varieties first, and then define schemes as just objects that only have that structure. And then we'll see later that those correspond to all rings. We can find, for every single ring, we can find one of these spaces that works this way.
So definition of scheme depends on which sheaf we're using, right?
The definition of...
I'm guessing. I've never seen this.
So a scheme is what's called a locally ringed space, which means it's a topological space together with a particular type of sheaf. A sheaf of rings that has a special property that, yeah, I won't get too into it. But when you take the ideal of things that vanish at a point and quotient out by it, you get a field. It's a maximal ideal.
So I guess which coordinate space and which sheaf do I need to pick to get back varieties?
We'll go over it. I'm not going to be able to explain it all right now.
Okay.
There's a little bit of discussion that goes into it. But yeah, that is what we will be talking about. I want to see the sheaves in their original habitat before I just like drop them on you.